Welcome back, students. Let us see video number 41 of chapter number 12 of physics, part number 2. In this video, we will see about alpha trajectory. Got it? To study the trajectory of alpha particles, we have to take few assumptions. Okay, which are the assumptions? Let us see. So let us see. Assumptions for the computation of alpha trajectory. Okay, first assumption was that here we have taken gold foil and this gold foil was very thin. How much thin? 2.1 multiplied by 10 raised to minus 4 meter. Okay, why this gold foil is taken as a thin? Because there is only and only one alpha particle get scattered from that gold atom. Clear? So gold foil is taken as a thin because of this reason. The scattering of alpha particle or you can say that only one alpha particle get scattered during the passage from the gold atom. Okay, so this is the first assumption. Okay, because of that thin gold foil, only one alpha particle is considered as a scattered alpha particle during the passage of all the alpha particles. Okay, second conclusion, second assumption. Only one alpha particle gets scattered. That is why only single atom of gold is considered. Okay, means only one alpha particle gets scattered, and for that one alpha particle we are going to take a single atom for the computation of trajectory of alpha particles. Let us see second conclusion. Alpha particle is taken as nucleus of helium atom, and we know that as it is a helium atom, it consists of two units, means it having charge. How much? 2e, and it having a mass equal to the mass of helium atom. Okay, then that gold having charge. How much charge? Ze. What is Z? Z is nothing but atomic number, and atomic number of gold is clear that the charge of gold is Z. The charge of alpha particle is 2e, means gold, the atom, the nucleus of gold is 50 times heavier than alpha particles. So this indicates nucleus is 50 times heavier than alpha particle, and because of this reason only throughout the experiment that thin gold foil remains stationary, remains steady. Okay, so because of this reason gold foil remains steady throughout the experiment. Okay, and then we will calculate the Coulombian repulsive force and Newton's second law. With the help of Newton's second law and with the help of Coulombian repulsive force acting between nucleus and alpha particle, we will decide the trajectory of that alpha particle, and that nuclear force, that Coulombian repulsive force is given by equation F is equal to K Q1 Q2 upon R square. Instead of Q1, charge of alpha particle, that is 2e, instead of Q2, charge of nucleus Z, and instead of K, it is 1 upon 4 pi epsilon 0. So this is the Coulombian repulsive force acting between that nucleus of gold and alpha particle. Clear? This equation also shows that this nuclear force depends upon distance. Means, suppose this is a nucleus. As alpha particle is away the nucleus, the repulsive force is less. And as it approaches the nucleus, the repulsive force increases. Right? And because of that reason, the trajectory of alpha particle may change. How it change, we will see after few minutes. So this equation also indicates that as distance r increases, or you can say that as alpha particle approaches the nucleus, the repulsive force decreases, or as distance decreases, repulsive force increases. And because of this reason, the trajectory of alpha particle may change. Clear? So these are the assumptions. Let us see assumption once again. The gold foil is considered as a thin gold foil. Because of that reason, only one alpha particle gets scattered along all the incident alpha particles. And due to this, only single atom of gold is considered during this experiment. Second, alpha particle. The alpha particle is considered as a nucleus of helium atom. And this helium atom consists of two units of charges, and the charges are 2e. As we have taken target nucleus as a gold, that gold having charge Z, where Z is the atomic number of that gold, and it is 79. So from that it is very clear that the nucleus of gold, that means nucleus is 50 times more heavier than alpha particle, and because of that reason the gold foil remains steady throughout the experiment. Clear? So by using this assumption we can compute the trajectory of alpha particle employing Newton's second law of motion and Coulomb's electrostatic repulsive force, and that repulsive force is given by the equation 2e charge of alpha, Ze charge of nucleus, that is gold 4 pi epsilon 0 r square. So as r decreases, the repulsive force increases and the trajectory of alpha particles also changes. Clear? Which type of trajectory of alpha particles have, that we will see after few seconds. Let us see for some time. Ready? So let us see. So these are the assumptions, and that assumptions may ask, maybe not, but it is useful for our logical questions. Okay? So now let us see which type of trajectory that alpha particles follows. See, in our textbook there is a one simple figure, but for our convenience we are modifying that figure. Why? Because just now we have seen here there was an equation. That equation indicates that as distance decreases, repulsive force increases and the trajectory of alpha particle may change. Got it? So to understand that things, we will modify that figure which is given in our textbook. Okay? Before that, we have to see about one definition. The definition is of impact parameter. What is impact parameter? It having symbol. Which symbol? B. It having definition. The definition of impact parameter is this. It is perpendicular distance of velocity of alpha particle and the nucleus. Okay, this impact parameter plays a very important role in the trajectory of alpha particles. Let us see. So we have to modify that figure. For that, let us say, suppose this is the nucleus of gold. So consider it is a nucleus of gold. Here, let us take one alpha particle. That alpha particle is moving without scattering. When it is possible? When impact parameter B is more. If impact parameter is more, at that time Coulombian repulsive force is minimum. And because of this reason, the scattering of alpha particle is less. So, in this case, the alpha particle move without deviation, means alpha particles is undeviated. When impact parameter B is more. Is it? Now one more thing. Suppose there is a head-on collision. Sir, it is a new word. Yes, it is a new word. What is head-on collision? Okay. During head-on collision, the definition I will speak once after completion of this topic. During a head-on collision, B. Impact parameter having minimum value. If impact parameter is minimum, vice versa of this. If impact parameter is minimum, the Coulombian repulsive force is maximum between alpha particle and nucleus. So, this alpha particle get incident on their nucleus, but there is a head-on collision. What do you mean by head-on collision? So, this is the alpha particle. When it collides, the angle between the trajectory of alpha and the surface of nucleus becomes 90 degree. At that time, the collision is said to be a head-on collision. Mind back, this definition is not there in our textbook, that we have taken from the reference book. So when there is a head-on collision, impact parameter is minimum. At that time, Coulombian repulsive force is maximum, and because of that reason, you got the idea, plus repel. And because of this reason, the alpha particle rebound back. Got it? So, there is a maximum scattering. And that maximum scattering indicates, or it gives the idea of nucleus, the definition of nucleus. Now, let us say the last thing of this. Here we are taking few points that indicates the distance r. Okay, so let us take this is the distance r1. It is far from the nucleus, and because of that, the scattering of alpha particle is less. As we go away, as we go near the nucleus, the scattering will be more. Clear? At this point, the scattering of alpha particle is maximum. Means here you will have the scattering of 90 degree. Means it gives the proof of that Coulombian repulsive force. We have obtained the equation of F. F is equal to 2E multiplied by ZE divided by 4 pi epsilon 0 multiplied by R square. And at that time, we wrote one sentence. As distance changes, Coulombian repulsive force changes, and because of that, trajectory of that alpha particles are also changes. Okay, so this is the simplest figure for your understanding. But in our exam, we don't have to draw this type of theory. You have to draw according to our textbook only, like this. Let us see. Okay, so in our textbook, the figure is very simple. I am repeating the same theory, same things. This is the nucleus of gold having charge Ze. Few of the alpha particles are moving undeviated because of that impact parameter. Impact parameter is more. That means B is more. If B is more, repulsive force is less, and because of that repulsive force is less, alpha particles having less scattering. Got it? Okay. Then you will find this type of figure. So here, point is away the nucleus. See, now the distance changes. Got it? Like this. So these are the trajectories. 1, 2, and here you will check the distance. So distance 1, 2, 3 and 4. These distances are different, and because of that repulsive force is different, and as you go nearer to that nucleus, repulsive force is maximum. So at that time the scattering angle becomes 90 degree. Now one thing remains, that is head-on collision. In the head-on collision, see, like this. In the head-on collision, the angle of incidence is 90 degree. Easy to understand. During that head-on collision, the angle of incidence of alpha particle is 90 degree, and because of that, it having maximum Coulombian repulsive force, and it rebound in a same direction. Means at that time you will say that theta value is 180 degree. Got it? So this is about trajectory of alpha particles. Right? And doubt? If you will have any kind of doubt, check the textbook, and then also you are not getting some idea, you are having confusion. Why? Because the topic is like that. It is very easy to understand, but not easy to digest. Try to digest the topics, and during that digestion process I will work as a right? Digestion fast thing is, don't worry. Okay? Have a look, enjoy it, good day.